The point now in these early days is to investigate physical systems of a sort that just haven't existed before. It's to make something that when you see or measure its properties, it's like, wow, atoms have never behaved that way before. Light has never behaved that way before. So the beginning of this is having few quantum things, whether they're electrons or photons or atoms, talking to each other in this quantum language, which if the system is open to the world, there's just too much noise coming in. Imagine you're walking along and trying to have a conversation. So they start talking and boom, in comes a ping pong ball and hits them in the head. And so that constant bombardment disturbs any train of thought about having this conversation in the quantum language. A simple way to think about it is in the quantum world, everything, electrons, are not little BBs, little tiny particles, little tiny bowling balls, but they're really waves. It actually goes up and down, just like a water wave. So if you have a nice, perfectly calm day and you're going to put your finger in and then have the waves spread out perfectly calmly, and that's like an electron moving through a solid. But if the wind's blowing, then you get all these other little wavelets that interfere with this beautiful single wave. Well, by the time you're through, you don't see the nice wave. It doesn't have any coherence left. That's famously formulated by Einstein 100 years ago. It's called the fluctuation dissipation theorem. If these fluctuations of things coming in to mess up the quantum system, then the atom dissipates its beautiful quantum stuff into the environment. So all you have is just this envelope of energy without the actual waves. And the quantum physics is in the waves. So typically, to have really interesting quantum phenomena, you have to just get rid of all the interactions, all the people out there throwing ping pong balls. You gotta get rid of that.
That is a lot of equipment.
Yes, it is. So what you see here is a source for atoms. We try to create a pipe that guide the photons and the atoms into that pipe. So there's no way they can avoid each other. They have to interact. So how do we do that? The way we do it is it generates a cloud of cesium atoms. We shoot it to the center of the chamber, and we create 6 laser beams. Inside this laser field, they form some kind of molasses. No matter which direction it goes, we always trick the atom, so they keep losing energy. Its motion gets damped, and then it moves very, very, very slowly. This chip sits at the center of the chamber. In this window, there's a 200 nanometer thick, 300 nanometer wide. We call it alligator waveguide. The reason is because it's 2 parallel beams, and then it's the inverse of the alligator shape. So this shape might look very weird, but we use these teeth to create a situation that when photons propagate along the waveguide, all these teeth, they create interference, then the speed of light is slowed down. And the intensity of photons is strong here, weak here, strong here, weak here, strong here. When atoms see strong intensity, it gets kicked out by the photon. It has repulsive force. So we can guide this atom into this kind of dark spot here. At the same time, we can send another frequency of light, which brights up at the dark spots. It's the magic of this kind of alligator waveguide. So we achieve both guiding the atom and then have them interact strongly with the photon. Otherwise, it would be like atoms are flying around and I shine a big white flashlight, just hope that my flashlight can hit the atom. But using this kind of lithographically patterned waveguides, we can create an array of these tiny little traps. So if one atom gets excited, it emits a photon. This photon can travel down to the waveguide, talk to another atom. And then this atom changes the property of this photon and then again propagate down the waveguide and then talk to another atom. By doing this, we can create a quantum simulator of many, many quantum objects interact with each other. And then if I just let the system evolve, what would the answer be?
We've done experiments, other people have done experiments where you can make a state where you have 2 beams of light and this one has a photon and this one has nothing, or this one has a photon and this one has nothing. And those 2 possibilities can exist at the same time. There's only one photon and it's in both places at the same time. And we've done experiments to demonstrate that that's true, that we really made a state like that. In our experiments, we took those pieces of a photon, if you will, it's called entangled, and we put them into a bunch of atoms. How would those 2 parts of a photon propagate? How would they see each other? The easy thing to say is this piece of the photon could be absorbed by the 5th atom, and that piece of the photon could be absorbed by the 35th atom. And then they would both come out. And then they would rattle around some more. And then this quantum pinball, if you want to call it that way, the photon bouncing around, or a photon in 2 pieces, or 5 photons in 25 pieces, that can get real complicated in the way the waves interfere as the photons run up and down, because they're not BBs as I've been describing them. What really happens is the photon can be absorbed simultaneously by all the atoms. And then each of the atom has, if there were 20 atoms, each of the atom has only a 20th of the photon. And now you'll say, which atom is it in? It's 1/20th in all the atoms at the same time. If I gave you this thing and you were going to play with it, it's got an input and an output on 2 ends. You can send light in, get light out, change the frequency of light. You can send impulses. You can look at how many come in and out. And you would say, being a trained physicist, what the heck is inside of there? And I would say, isn't it neat, you know? The point now in these early days is not let's make a quantum computer. It's to build quantum systems that are surprising with characteristics that just haven't existed. Now the boundary has pushed into very different parts of physics than I've ever been comfortable with or knew anything about. So that technology of how you do that, how you build those, my group knew nothing. But that's what you're supposed to be doing, you know? If you want to be at the cusp of the future, you have to be willing to fail. We've come up some climb and it didn't work. You better go down, try another way. You better believe it's scary. But it's an exhilarating intellectual adventure. In my position, wow, it's a privileged position to be able to explore. So if you know what you're doing, don't do it.